All right, shall we get started? So before we begin with photons and sensors, let's do some best photos. So this is from assignment 2, Sports in Action. And the first one is Mandy Guo, Freeze the Action. A very nice picture of a soccer player. I'll talk a little bit later in the course. I'll give a lecturelet on sports photography. Okay, so for Blur the Background, there's a great shot by Florian Kainz. This is not like the first picture you would take from the Google bus. He worked on this actually for quite a while to be able to take this picture. It means it can't go over any potholes, it has to be perfectly smooth. He did a lot of trials to get this right. Ellie Patton, blurring the background and part of the foreground. Not exactly one of the requirements, but it's a great picture. And then a number of motion sequences. So Alice Liu, it's a great sequence of lighting a match. Alan Yang, another motion sequence. So these are all superimposed on a single image. Another Florian Kainz, multiple exposure. So this is hard to do. It's not really a multiple exposure where you just expose the camera because it's a digital camera. He's using Photoshop. He's creating mats manually in order to layer each image on top so that the right ones occlude each other. It's not easy to do a picture like this. So I don't know if this qualifies as burst photography. It's an animated GIF, of course. But I think the best part of this is the comment by Zalman. It says it needs to be a meme gen template. So your next assignment is figure out what that meme gen template would say. What's the framework of words for it? All right. So today we're going to talk about photons and sensors, and we'll apply the theory that we talked about last time for sampling. So we'll now kind of begin, for the rest of the course, a trip down the camera pipeline, akin to the trip down the graphics pipeline in computer graphics. So starting from the sensor, we'll talk today about analog to digital conversion, where voltage is turned into numbers. And then there's a whole lot of post-processing. We'll talk only about demosaicing today. We'll talk about all the rest near the end of the course. And then storage. So it's hard to talk about any of these authoritatively because every camera uses different algorithms and they may be proprietary. So I know some processing pipelines. I certainly know the cell phone processing pipeline, and I can guess at what the single lens reflex cameras do. So here's an example for each of these categories. There's an older Canon sensor, an older digic processor, so that's the actual programmable processor. And there's a flash card, and here's where they actually go in a camera. It's a little fast and loose here because the parts are from one camera, but the cutaway is a different camera, but they don't change that much. So you can see that processing board down there, and the flash card, and the sensor. All right, so what we'll talk about today is photons to charge, and then to numbers. So we'll talk about getting the charge off the sensor. We'll compare the two major classes of sensors, CCD and CMOS, and we'll talk about the analog to digital conversion briefly. And then there are a few supporting technologies, the micro lenses and the anti-aliasing filter, which fit right into the theory that we talked about last time. And then we'll talk about color. All right, so another picture of a famous scientist. The fact that we can take digital pictures is dependent on the photoelectric effect. So Einstein published this paper in 1905, and his Nobel Prize in 1921 was actually for this paper, not for E equals mc squared, or the theory of relativity. It was for the photoelectric effect, because they considered the other to be too speculative. So here's the equation. It basically says when a photon strikes a material, an electron may be emitted, so with some probability. And the probability rises with the energy of the photon, which is Planck's constant times the speed of light over the wavelength. So there's no notion of the color of a photon. There's only its energy. And so if you look at the formula, you can see a shorter wavelength, like blue, will have a larger energy. And so that's where the color comes from. There's also no notion of brighter photons. There's only more or fewer of them. So energy of a photon and the number of photons is the variables we care about. All right, so as I said, not all photons will necessarily knock an electron loose, and whether it does or not is the quantum efficiency of the device. So here's a graph from the Hubble Space Telescope. This is wavelengths in angstroms, so you can think about that as 200 nanometers, 400 nanometers. And here's the DQE, which, what is that, detected quantum efficiency, so it's empirically measured. And you can see it's most sensitive around 600 nanometers, which is sort of a greenish red. And so it's just the number of electrons over the number of photons. So here are some actual figures. The human visual system is surprisingly low. We can detect a single photon sometimes, but a lot of them are lost to scattering. So the quantum efficiency is low. More is lost due to scattering as you get older. So a digital camera, maybe something like 50%. The best back-thinned CCD sensor might be 90%. So that's sort of the range of quantum efficiencies. So what I mean by back-thinned is, for many years, the design was this one, which was that the light went through all the metal layers and then struck the silicon. As I'll show a little bit later, those metal layers kind of get in the way. They cause what's called pixel vignetting. And you can improve things by turning the chip upside down. Now, that's not as easy as it sounds, because this is very thick, and this supports the circuitry. So you have to glue it to something else and then grind away, essentially polish away the silicon until it's thin enough that the light can come in the back. And then it doesn't have to go through the metal layers. I'll talk about the color filter array and the micro lenses a little bit later. So at this point, most, a lot of sensors are back-thinned. Cell phone sensors especially. All recent iPhones are back illuminated or back-thinned, called BSI. Okay. Oh, by the way, so this is actually much thicker here. And then it gets thin when you turn it upside down. The diagram's a little bit misleading. So pixel size is important. And an easy way to understand that is just think of a rain gauge. If I want to measure the amount of rain during a rainstorm, and we can think of the photons arriving as raindrops, then I'd like this to be as wide as possible and to integrate over the entire rainstorm, so as long as possible. Both of those will decrease the variability in the number of raindrops that I measure. We'd also like this to be tall so that it doesn't overflow during the rainstorm. So all of those are important. The latter is important to dynamic range. We'll quantify that a bit later. So integrate over space and time. So typical sizes. This is that one point-and-shoot camera that I said was particularly good and maybe still worth buying in the current landscape. And there's a Canon 5D Mark III. So its pixels are much bigger. It also has a deeper well. Oh, by the way, the units here are femtoamperes. So 1 electron is very small. Okay, so the height of that rain gauge is what's called the full well capacity, how many electrons it can store, literally. And here's a graph. So this is the pixel pitch, which means the distance between pixels on center. And here is the number of electrons they can store. So 50,000, 100,000 electrons. So why isn't it exactly along a curve? Well, there are variations in the architecture of the pixel. It might not fill the entire space between pixels. That's called the fill factor. And there are other, whether it strikes metal and what else might be in the way, so that's why there's some variability, but it follows a general curve. And so here's an example. I don't know if you can see. This one is noisier than that one. The one on the top is Canon 1D Mark II, and the one here is a point-and-shoot camera, Canon S7D. So too many photons causes saturation. We'll talk about dynamic range a little bit later. All right. So laundry list, it's a practical device. Things go wrong. One of the things that goes wrong is blooming. So blooming means charged electrons spilling over into adjacent pixels. And so the sun is not that big unless there's a thermonuclear war going on. And so this is blooming. This can happen on either of the two major kinds of sensors, CCD or CMOS. Don't confuse this with glare or other artifacts. Glare is occurring in the optics. This is occurring on the sensor. Sometimes it's hard to distinguish different artifacts. So for example, if I show you this one, is this blooming? And there's the sun, and it looks like it's kind of spilling around. No. What do you think it is?
Combination of the defocus and the scattering of the clouds.
Yeah, so it's mainly the defocus. And the simple way to think about that is, in plan view, there's the sky, and here's a horse's leg, and the lens, let's say, is over here. And so one pixel, and let's say we're misfocused, so we're focused on this plane here. So that pixel sees only horse's leg. It's not focused on the horse's leg, but it's integrating over all these colors that are probably pretty similar. So it's going to be a dark pixel. But look at, here's the sensor. Look at this pixel. So this pixel is focused here, and some of its rays strike the horse's leg, but others of its rays strike the sky. And so it's going to be an integral of all of these colors for that pixel. So it's going to look like part leg, part sky. And that's exactly what's causing the blur area there and the apparent shrinkage of the horse's leg. That's a focus effect. It's not blooming. People buy that. Okay. So here are the two major sensor types, CMOS and CCD. I'm not going to go into these in depth. I'm not even qualified to go into them in depth. But the basic idea is there is a place where the electrons are stored, and then there'll be an amplifier and some way to put the charge onto a line that goes out. Typically, they read down in columns. The CCD is a little bit more complicated. It's got a charge, a place where the electrons are stored, and then a mechanism for transferring them over into this channel, where then they are read out along that channel. They can all be shifted at once, and so a CCD can easily do a global shutter instead of a rolling shutter. There are ways to do that in CMOS as well. It involves more transistors. This is a bit noisier, but getting better all the time. This is a bit cleaner. This is faster. This is slower because of the readout, which you have to do by taking it from bucket to bucket along this kind of bucket brigade. And so CMOS is winning, basically, especially for consumer cameras, where speed is important. So here's, right, so these are kind of an old camera, Nikon D40. So I think the last Nikon that used a CCD was the D3000. Now they're all CMOS as well. And Canon SLRs have been CMOS for quite a while. Question?
Is noise related to the electrons?
Right. So I'll have a whole lecture on noise. There are many sources of noise. One is the variability in the number of electrons, and we'll define that. That'll be photon shot noise. But there's noise that happens when you read it out. There's stuff that happens in the pixels when you're not looking. We'll go through every single source of noise. I may or may not get to that today. If not, then we'll start it. We'll do it next week. Yes?
When you say speed, do you mean like being able to do a burst of shots?
That's right, because you have to read it out.
Okay.
So the readout speed is very important. While I'm here, let me just see if there's anything on the door. Right? No, nothing. Okay. Question?
The flip side of that question, I mean, if I were a landscape photographer and I didn't care about speed, would I have a sensor preference?
You know, would you have a sensor preference if you didn't care about speed? You know, these days the CMOS sensors are really pretty darn good. So even the very best pro Canon cameras are CMOS. I would, astronomy still uses CCDs. One of the problems with a CCD is that you can't convert it to a number, the analog to digital conversion, right on the chip. You have to do it on a separate chip because of the way the process works. So it's cumbersome to do that and more expensive. And so when you're architecting a system, you try to avoid that. So here's a little gratuitous animation showing that bucket brigade. So you can see the voltages being applied to different pads. Here are a bunch of electrons. There's the timing for each of these pads. And so I think phi2 is going to be turned on, and that begins to attract electrons. And then phi1 is turned off. And then phi3 is turned on, and that attracts more electrons. And so you can see how the bucket brigade kind of moves along. That's how the charges for each pixel are read out. It's pretty amazing that such a thing even works. So it doesn't work perfectly. And because it doesn't, if the electron wells are full, there's a tendency for that bucket brigade to slop over and to pollute the pixels on the way down the column. And that's called smearing. It only happens on CCDs. It does not happen on CMOS because of the way it's read out directly onto a line. Okay. So this is an orange tinted slide for my Stanford folks. Let me go very quickly through how analog to digital conversion occurs. I won't go into detail. The basic idea is there's a voltage divider. So if you're not an EE, what that means is here's ground, here's some positive amount of voltage, and there are a bunch of resistors in series. And so what that circuit means is that it will divide that voltage into steps. And so if there are 256 steps from 0 to 5 volts, then each step will be a 50th of a volt. So if you tapped in here, you'd measure 2/50ths and 3/50ths of a volt and so on. Then what you do is you take the signal from one of your pixels. So let's say we're doing a CMOS. So we've read it out down the line, and then those electrons go into this circuitry at the bottom of the column. And there might be one of these for each column if you want to do this fast. And then it gets compared with the voltage at each step in this ladder. And that outputs either a 0, saying that the voltage was greater than the input, or a 1 saying the input was greater than the voltage, right, on the ladder. And so it's, in this case, it'd be 100 ones and 156 zeros if the incoming level were 2 volts, which would be the 100th step. And then that goes into a decoder, which turns it into the typical binary number. And it's as simple as that. So practical systems may use a different architecture where they'll do a coarse ladder with fewer steps in it, compute the residual, and put that into another ladder, or even the same ladder over and over again. So there are a lot of different architectures, but the principle of it is this ladder of voltages from a sequence of resistors. And as I said, there may be one of these analog to digital converters for every column, so that you can read off a whole row at once. They'll each go through their separate analog to digital converter, and they'll go out. So how many bits does this need? So one thing to keep in mind is what you're going to do with that number later. And you may remember that I talked about this nonlinear mapping, ADC output, and let's say 8-bit JPEG. And so between these two, there is this nonlinear function, this gamma function that I talked about, which was introduced originally because display monitors did the opposite, so cameras ought to do this. There is another reason for it. It better matches the sensitivity of the human visual system. Right now, I want to talk about a third issue, which is quantization. So suppose we divided this into, let's say there were only 3 bits in our ADC. So there'll be 8 of those, and there'll be a whole bunch of there'll be 256 bins here. So if you see what's going to happen, the first bit, the first value will be all the way up here. And those will never get populated. You'll never get that output intensity value. Excuse me. And the same thing here. And then, of course, these will get squeezed into a single value. So you're losing precision. You're going to get quantization artifacts, contouring in particular. So it's important that this not only have a reasonable number of bits, but it should have more bits than this. And if you work it out, given the particular shape of these gamma curves, it should be, if this is 8 bits, this should be more than or equal to 10 bits. And SLRs are more than that, but it should be at least 10 bits. And so cell phone sensors will have a 10-bit output, at least. They may have more. Okay. So fill factor. As I said, there may be a difference between how big the pixel is relative to the spacing between pixels. And there are all kinds of things that happen. This is a front illuminated. So there are these metal layers that you see through here, and the light has to come through the top. And while this looks very well mannered, you can easily imagine that if you look at, so these are micro lenses, I'll talk about those in a moment. You can easily imagine that although this is well mannered, the edge of the pixel, this is 1 pixel, could run into a bend layer or something like that and get what's called pixel vignetting. So the design then of these micro lenses is extremely important. And in fact, if the angle here of the chief ray, which is this ray, is too great, you have real problems. So imagine all the way on the edge of the field of view. And in particular, imagine one of these mirrorless cameras where there's no mirror box, so the distance between the lens and the sensor is smaller than it is here, because there's this big flippy mirror in the single lens reflex camera. So what you're going to end up with is very oblique rays hitting that sensor. And you've got to do some fairly heroic things to engineer it. So here's a Leica, which is a full frame camera, so 24 by 36 millimeters, without this mirror box. And so the chief ray, which is the center ray here, strikes at quite an angle. And so what they do is they actually shift the micro lenses. So there's a lot of very subtle design that goes on here to try and avoid missing the pixel or polluting the adjacent pixels, what's called crosstalk. There's a lot of design that goes on here. So let's talk about these micro lenses from the point of view of the sampling theory that we considered last time. So integrating light over an area instead of just taking a point sample, we know will reduce aliasing. And so what these micro lenses do is they capture more light, first of all, and they also make sure that the fill factor is equal to the pixel pitch. So no photons get lost anywhere. So it effectively convolves the image with a pre-filter. Sorry, I didn't say that quite right. The integration over the pixel area is already convolving it with a rect function. The micro lenses improve that by making sure that the fill factor is 100% or close to it. So it improves that rect filter and gathers more light. Integrating light over the exposure time, by the way, is another rect filter. It's a rect filter in time. It also captures more photons, so it reduces noise. And then it convolves the scene with a temporal pre-filter, effectively a 1D filter. So in movie making, there's maybe a rect function like that, but then there's some gap because you have to pull down the film to the next frame if you're doing a traditional celluloid movie. So let's think about this rect function. How good a pre-filter is that? Does it remove all the aliasing? And let's consider the spatial case. The temporal case is going to be similar. Suppose you have a pixel grid like this, and let's just consider 2 rows of that. And suppose that the object that we're trying to measure is a very shallow line like this that's, say, solid blue. So it's blue all along its length. So now the question is, what intensity, and let's say that we have perfect rect filter, which is equivalent in the case of pre-filtering followed by point sampling with just averaging, which is exactly what a camera does. All the photons that fall in that one square. So what's that going to look like? Well, let's look at just row A and make a plot of what that's going to see. So the intensity along A. It's going to be 0 here, and 0 here, and then it's going to begin to climb. So that's this area here. It's not as wide as the entire stripe. Now the stripe is fully inside, so some maximum. And then look at that. It's the same intensity. And then it begins to drop again. Okay? So do people see what that looks like? So that means that at least during some period here, there's no change in the intensity that the pixels record, even though this stripe is continuing to slant upwards. And the same thing will happen in the other rows. And so the appearance you'll get if you were to display this is, this will be some color, begins to get a little dark, the same half darkness, and then even, oh, no, sorry, then this gets lighter again and lighter again. So if you kind of stand back and look at that on a raster display, what you'll see is something that kind of looks like that. It'll have this sort of ropey appearance on the raster display, where these horizontal sections correspond to the pixels in which nothing changes, because we used a rect function. This is aliasing. It's high frequency content, a very thin feature masquerading as low frequencies, which is the rhythm of these little bumps or ropey appearances. So you can still get aliasing. Now the same thing can happen in time. Imagine that this were a small blob, like that, that's moving to the right over time. It's going to do exactly the same thing. You'll see a transition when it's in this position, and then through those positions you'll see nothing change. And then you'll see a sudden half transition, and then you'll see it be in that pixel. So it'll go choop, 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 like that. So that's a failure of the pre-filter to remove all of the high frequencies. So because of that, we introduce anti-aliasing filters on top of the microlenses, in addition to the microlenses. And so cameras have these. There are a variety of technologies. Here's one, which is to have thin layers of birefringent material which split like a calcite crystal, will create little copies of the image. And typically, there are a number of layers. This is bluish because it's combined with the infrared cutoff filter. Never mind that for now. And so it'll typically create 4 images. So if you think about that from the point of view of spatial convolution, which is what an anti-aliasing, what a pre-filter is supposed to do, it's a 4-tap discrete convolution filter kernel. So it's effectively doing convolution. It's replacing 1 copy of healthy eating with 4 copies. It's discrete because it's just going to be 4 copies of the healthy eating, 4 tap, and this is only a 2 tap here, and the kernel just means that's the non-zero part of it. So it looks like a kind of a crude anti-aliasing filter, but actually it's enough to really help. And so it's enough to help get rid of this ropey appearance. And so cameras have these. You can remove them. So we talked about that briefly in an earlier lecture. $450 plus shipping, probably has changed by now. Now you don't need to actually send your camera off because you can buy the higher end SLRs with or without an anti-aliasing filter. So look at the ground. It's a little bit softer here than it is here. I think I've got a blow up. You see it's a little bit softer here than it is when the anti-aliasing filter is removed. So you can improve sharpness by removing this anti-aliasing filter. But beware, you'll get aliasing. And so here's an example of a different part of the same shot. And look at the moire patterns on the air conditioner. Here's a blow up. See these diagonals there and there? That's a pattern that doesn't exist on the air conditioner. That's high frequencies masquerading as low frequencies due to insufficient sampling rate, which we can't help, and an insufficiently powerful pre-filter. So here's a more severe example of that. This is a picture of a lens taken with a Nikon D800 or the D800E, which has the anti-aliasing filter removed. So those are fairly, these don't necessarily produce subtle artifacts. They can be fairly large artifacts because once it's masquerading as a low frequency, it can be very low and you can easily see it. Question?
So how is that different than like at just blurring where you can do that in software?
Very good question. So how is that different than blurring in software? That's called post-filtering. If I were to take this image into Photoshop, just the way you see it here, and blur it, that's not going to get rid of that. The low frequencies have already been produced. Once there is aliasing, you cannot get rid of it by post-filtering, unless I blur so much that the whole image goes away.
Right, so what did that glass filter do?
So that anti-aliasing filter is before, it sits on top of the sensor. And so it's before the sampling done by the sensor.
So it's blurring, but before the
Before the sensor, and that's absolutely key. So pre-filtering is done before sampling. Post-filtering, which would be blurring this in Photoshop, is done after sampling and cannot remove aliasing. Glad you asked that question. Okay, so any other questions? Talked about CCDs, CMOS, talked about integrating to both improve dynamic range and to avoid aliasing. We use micro lenses to do both of those, and then we also use an anti-aliasing filter to improve on the pre-filter. And then the same thing happens over time. Question?
So Canon in their latest DSLR say they can apply a post function that can remove the effect of the anti-aliasing filter. What are they talking about?
They can remove the effect of the anti-aliasing filter. You mean sharpen it again?
Yeah.
Yeah, sure. You can sharpen. It isn't exactly the same. If the anti-aliasing filter were perfect, it would remove those high frequencies entirely, replacing them with an average. I showed that with a checkerboard in computer graphics. If the frequency is completely gone, there's nothing you can do. You don't even know what information was there. If it's an imperfect anti-aliasing filter, then you might be able to do a restoration. That restoration will probably enhance noise. So it's not a totally unreasonable claim, but there are trade-offs. Question?
Would it be possible to do two shots, one with the anti-alias, one without it, and then sort of merge them into a...
Oh, there's an interesting. What he's proposing is taking two shots, one with and one without the anti-aliasing filter. So I've thought of, people are talking about lots of architectures with multiple shots and multiple cameras. That one I had never heard before. It'd be a little impractical. You know, how would you actually get rid of that anti-aliasing filter? You'd almost need a beam splitter with two different sensors. So you would use the shot without or with the filter. Yeah, I'm not sure how well that would work because the aliasing was really pretty severe. So it's not letting in frequencies you can trust is the problem because they might be aliased. So I think it'd be pretty hard to get something reliable out of that.
It actually might be possible if you high-pass filtered the anti-aliasing, the lack of anti-aliasing filter image, gave that a very, very high frequency
Boost.
passband
Yeah.
and cut all the low frequencies so that it wouldn't be necessarily practical, but it might work.
Yeah, he's suggesting a high-pass filter on the anti-alias version.
On the non-anti-aliased.
On the non-anti-aliased.
Right. Because the non-anti-aliased.
Oh, because the aliasing is low. Oh, yeah, but
I don't know
the
how much you would gain.
the aliasing artifacts, they're high frequencies masquerading as low frequencies, but how low they are
Depends on
it depends on a lot of stuff. You should remember that moire pattern. I could make that so that the alias pattern you saw was almost as high frequency as the actual screen of lines. So, question in the back?
Is there a numerical way to describe the cost of an anti-aliasing filter and reduce sharpness of the frequency?
Yeah, you can do a frequency analysis, which is a little bit beyond the scope of these lectures. If you know exactly where those taps are, in other words, what the birefringence filter does, you can analyze that in the Fourier domain. Absolutely. Let's see if there's anything on the dory. Why do stacked CMOS sensors have better signal to noise than non-stacked? I'm not sure what you mean by stacked. I don't know if that means Foveon or not. Why don't you, because I'm going to talk about the Foveon very shortly. If that's it, then I'll reach it. If it's not, then I misinterpret your question and you should ask it again. Okay, so let's talk about color. So silicon detects all visible frequencies reasonably well, as in addition to infrared, which we do not see. But once a photon is struck and knocked an electron loose, you can no longer distinguish wavelength. All electrons look alike. There's no such thing as colored electrons. And so if you want to detect color, you want to discriminate color, you need to do something before it turns from a photon to an electron. So you have to select the frequencies that reach particular detectors or particular parts of the detector. You can block them with a filter, or you can separate them with a prism, or a dichroic is an interference filter of some kind, similar to the anti-reflection coatings that I talked about earlier in the course. So 3 spectral responses, 3 different kinds of pixels, 3 different layers is enough, although some cameras have 4 in order to achieve improved dynamic range. Why 3 is the magic number is because of the variety of cones in our retina. We'll talk about that in great detail in a couple of weeks when we talk about color. As I said, it's also sensitive to near infrared. You usually block it. That's the bluish color of that anti-aliasing filter I showed. If you remove it, you have a near infrared camera, or you have a visible plus near infrared camera. All right, let's just have a little bit of fun here. Who made the first color photograph? No fair if you've been looking at my Stanford notes. Anyone know the answer? It's surprising. It's Maxwell. The same Maxwell from Maxwell's equations. He actually did the first experiments on color matching, so I'll come back and talk about him when we talk about color theory. All around smart guy. He shot 3 images through filters and then simultaneously projected them so you could see a color image. All right?
What is that?
It's a ribbon, some kind of Christmassy ribbon, I guess. Who made the first color print? I know, you're not going to know the answer to that. It's Louis Arthur Ducos de Huron. And he shot through filters and printed with color inks. And he experimented with different color inks. I'll come back and talk about what are the right colors of inks when we do the color lectures. But perhaps more famous now is Sergei Prokudin-Gorsky, who did these spectacular high-resolution separations. And he tried to also simultaneously project them, but the available technology couldn't have done a very good job on that. We can do a great job digitally by digitizing his 3 different pictures and combining them back together. So this is a very early color picture. It's 1911. But they're spectacular, and you can find a lot of these online from him. So here's an interesting one. What's going on here? Why is there shimmering on the water?
Because the water moves.
the water moved between exposures in sequential exposures, right? Okay. First color movie technology.
Practical or
That's a good way to ask. So, right. So before Technicolor, there was this Kinemacolor, which was alternating red and green filters over time. So a total frame rate of 32 frames per second, and then projected through alternating red and green filters. But the first practical one was Technicolor. Technicolor was initially just two colors. So it's a beam splitter leading to two filters. So that's simultaneous capture, not sequential capture like the previous technologies that I showed. And it's two strips of film that you would then cement together and run them through a projector. And what's interesting is that it almost seems to you as if it's that these are full color. You don't immediately say, oh, where is blue? It actually looks kind of natural. So this reminds me, of course, of Land's Redneck's theory of vision, where two colors turn out to be sufficient for a lot of contexts because of the way the human visual system interprets color. And then it was used for cartoons. So, sorry, then the three-color process was invented, also from Technicolor, and used for cartoons and then later for movies. So a little gratuitous movie in here. It'll come around in the animation just a second. So these were often shown as shorts before feature-length movies. And this must have had a pretty dramatic effect on the audience because they'd never seen a full-color movie of any kind before. And what's interesting also is that it's better preserved than the single-strip color movies of the 1960s because they're separate black and white negatives for each of red, green, and blue. And those preserve well. The color doesn't fade. And I'm sure you've all seen Wizard of Oz, where it starts in black and white and then switches to this wonderful new technology, three-color Technicolor. It must have had a pretty dramatic effect. All right, enough of that. First consumer color film. Anyone know? Kodachrome. Yeah. And lots of very famous photographs taken with Kodachrome. No longer available. How about the first color television broadcast? It was the Ed Sullivan Show, broadcasting the Beatles. This is not the famous Beatles on the Ed Sullivan Show. That was in 1964, not 1965, and it was in black and white.
With me that the city never has witnessed the excitement stirred by these youngsters from Liverpool who call themselves the Beatles. Now tonight, you're going to twice be entertained by them. Right now, and again in the second half of our show. Ladies and gentlemen, the Beatles!
Close your eyes and out this.
All right. So there are competing standards for color television. The National Television Standards Committee, phase alternating line, I think is what that means. And sequential couleur mémoire. They have different line rates and different cycles per second because of the current in Europe versus the United States. This is right on the hairy line of being detectable. So when I go to Europe, I think I see the televisions flickering. And the French say, oh, you're crazy. They don't see it.
Just a fun fact about the 30 frames per second. It was because of the introduction to color that we actually used 2997 because of interference potential with the audio.
Right. He's saying that in order to avoid interference with the audio signal, we shifted the 30 to something slightly different, which is 29.97 or something like that, frames per second. So these were competing standards, and so you would have to expect that they picked on each other. Okay. So let's get serious again. So we've talked about the field sequential already. Let's talk about the other technologies. So 3-chip is commonly used in professional broadcast television cameras. And the basic idea is that the light comes in and is split in some way using a prism or dichroic into 3 separate images, which are then focused onto 3 separate CCDs, which have to be exactly the right distance from the optics, each one of them, so that they're all in focus at once. So it's a pretty delicate arrangement. And you can see that here. There's the red going out, and the green, and the blue. So as compared to filters, there's a big advantage here. No light is thrown away. No photons are absorbed by filters. Instead, they're split off. And so it performs reasonably well in low light. But it's expensive, and it complicates the lens design. And maybe the lens here had to be a reverse telephoto in order to give it a little bit more room for all this dichroic stuff in the back, possibly. So a number of people have asked about this. This is the Foveon stacked sensor. And the idea here is that light penetrates to different depths in silicon depending on the energy of the photons, which means the wavelength, which means the color. And blue doesn't penetrate as far. So sort of like your skin, if I point a laser or a bright light at my skin, the red will go further. And so the top gets mostly blue, and then green, and then red. And so you could separately detect them, and that means you could get color at every single pixel. The problem is, so it has fewer moire artifacts because you're not looking at red here and then red here, and not sensing red in between, as you do in a Bayer mosaic, which I'll show in a second. But possibly worse noise performance, which might seem a little surprising, but the problem is that silicon is not particularly sensitive to blue. And then the red has to go a lot further, and so the noise performance of these is not great. But you can buy them. Oh, did I show that? Yeah, there's a Sigma camera. You can still buy them. And Dick Lyon, as well as Roman Levkov and my team, worked on the Foveon camera. Okay, so what all the cameras you're going to run into as a photography camera have is a Bayer mosaic, like this. So that means there's some kind of pattern where this senses only red, this senses only blue, and these are each separate pixels. So why are there 2 green pixels and not 2 red and 2 blue? Human
eye, right?
Sorry?
So aren't we more sensitive to
Yeah,
green?
exactly. We are more sensitive. So when we talk about color theory, we'll talk about this so-called luminous efficiency curve in more detail. But the basic idea is we're more sensitive to green. And you'd like a color camera to roughly match the sensitivity of the human visual system. I'll show an applet that quantifies that fact. So that said, you can play games for a variety of different reasons. Here's one that Sony proposed that has this emerald pixel. And the idea is it is letting through a lot of light. It doesn't filter out too much light. It's a very light emerald color. And the less photons it absorbs, the more efficient it can be. The clear pixels try to do the same thing. So that's red, green, blue, clear. So clear means no filters, more light gets in. So these days, a lot of cell phone manufacturers are experimenting with color plus mono. Right. So the Huawei P9, I guess, is color plus mono. I haven't actually seen it myself. But the mono sensor won't have any color filters. And so none of the light is absorbed. And so that one sensor should be roughly 3 times more sensitive than a color. And if you put the two together, it should be 4 times more sensitivity for light, more or less. There are problems in aligning those together. We could talk for quite a while about that. So here the idea is to do it on one sensor. But the problem here is that then you'll get, if you look at the red, it's not sensing red very often. So the frequency response to red objects is going to be relatively low. So there are lots of trade-offs in these alternative mosaics. So here's what typical red, green, green, blue Bayer mosaic looks like. And so if we zoom in really closely on her, and then we look at what comes off the camera originally, it looks like this. So you can't actually see that even in Photoshop. Photoshop doesn't let you look at this. You have to use a program like DC Raw. That's the actual raw image. There's no color there. They're just intensities in different pixels, and you have to know that one of them is the red, one of them is the green, and one of them is the blue. So the reason this looks like it's kind of little dots on a sea of a darker color is because her flesh is mostly, it's probably the red, actually. But you can see more of a variety in her eye. So if we only sense red or green or blue in a pixel, then we have to interpolate to get the other colors that we're missing. And so that's a process called demosaicing. It could be as simple as a linear interpolation, just an average. But what you prefer to do is not average across sharp edges in the scene, where it might be a completely different color on one side than the other. And so demosaicing algorithms are more complicated than that. They try to detect edges and not interpolate across edges. There are lots of algorithms that I could point you to in the literature. We're not going to go through those in detail here. But the important point for you to know is that 2/3 of your data is made up, because at each pixel it's only sensing red or green or blue. So selecting filters, dichroics, or penetration depth in the case of the Foveon, and measuring color requires some kind of a trade-off. It's either you're trading off against capture duration, or you're trading off against weight and expense for the 3 chips, or you're trading off noise, or you're trading off spatial resolution. Any questions about this?
They
Yeah.
mentioned something about Foveon, Fuji X-Trans before, and they use a non-Bayer filter. It still has probably the same number of green, blue, and reds. They just arranged in a larger pattern. But
Right.
They say that they can then remove the antialiasing filter. They don't get as many more.
There are a lot of claims that these manufacturers make about different arrangements of mosaics, different stacking. It's always, whenever say they can remove this effect completely, you should be suspicious. They can make a different trade-off. All right, let's see. Zalman, people have proposed mechanical anti-aliasing. Oh yes, basically vibrating the sensor like this, using a piezo. The same piezo that would be used for stabilization of the image could also be used as an anti-aliasing filter. We'll talk about stabilization in a week or 2 weeks. Well, this would allow 2 shots, one with and one without anti-aliasing, is what he's saying. One can also get the effect via diffraction from a small aperture, because it's blurring out a little bit. Or you could also just defocus the image. So there's a lot we haven't talked about yet. We haven't talked about dynamic range noise. And we haven't talked about the spectral characteristics of the filters or practical demosaicing methods. This we're not going to talk about. The spectral characteristics we will talk about in great depth. And I'm about to start talking about that. Okay? All right. So given the time, I think the best thing to do is I'm going to switch to the noise lecture, because we still have 20 minutes. So let's see how far we get in noise. And I still haven't done the active autofocus, but it's a relatively minor topic. We'll fit it in as we can. The fact that I'm not going to be here on Monday, there's guest lecturers on Monday, has forced me to reorganize a little bit. So let's see if we can get going on the noise in ISO. All right, so we'll talk about examples of camera sensor noise, and we'll talk twice about the signal-to-noise ratio. Once kind of qualitatively, and then we'll list all the different kinds of noise sources, and then I'll do it again, and we'll get very specific as to which sensors have which kinds of noise and which ones hurt you under which shooting conditions. And ISO is gain, and we'll look at how that affects things. And then there are multiple ways of denoising. We'll talk mainly about those later on in the lecture. All right, so first let's make sure we can recognize noise. So this is an old cell phone that had a surprisingly good camera, the Nokia N95, just before the iPhone came out. And if we look at it closely, we see this. That is not noise. It's not noise alone. What it is noise triggering the JPEG compression, which we'll talk about in a later lecture, to pick inappropriate basis functions for the compression. Anytime you see something like this with a rhythm of 8 by 8 blocks, you should immediately suspect JPEG compression artifacts. And indeed, so those are 8 by 8 pixel blocks there. And you can see that those blocks, the block boundaries kind of continue down, and then you can see various things happening. So this is JPEG's attempt to compress and efficiently and properly represent all the noise. That's what's causing that. So let's look at images without JPEG compression. So let's look at the raw images after demosaicing. So here's a Canon 5D Mark II. It's a 1/13 of a second exposure, but there should be no motion blur because I put the camera on a car to take the sunset picture in the Sierras. I have a fairly high ISO, at least for the Canon 5D Mark II. And so we'll see plenty of noise if we zoom in. And let's zoom in even more. So that's noise. And that's the kind that we need to talk about. So there are several different kinds of noise. The most important one for us to talk about is photon shot noise. So photon shot noise is a variability in the number of photons that arrive on each pixel on each exposure. It will vary from pixel to pixel, and it will vary from exposure to exposure, even if the scene you're looking at is completely uniform and nothing changes over time. Excuse me. So this is governed by a Poisson distribution, which is this. So it expresses the probability of rare events. Rare meaning, if a photon strikes my sensor, the probability that a photon will strike my sensor a little bit later has not been measurably reduced. There are plenty of photons in the universe. And for that, the Poisson process is appropriate. So it occurs with a known average rate and independently of the time since the last event, which is what I had just said. So here is the Poisson distribution. And so what that's saying is, on average, lambda events will occur in a certain interval of time, but there's some probability that a different number will occur rather than lambda. And the probability that k events will occur instead is given by this formula. So the easiest way to look at that is let's look at the probability density function. So this says, let's look at just the black curve. So this says, this is for lambda equals 10, meaning the average number of photons that will strike the sensor is 10. But there is a probability that only 7, that should be down here, 7 photons will strike the sensor instead. And that probability is non-zero. It's 8% or whatever it is. Actually, the probability that exactly the average, the 10, will strike the sensor is itself relatively low. Usually it'll be some different number. And if the lambda is different, then it has different shapes. So it's a function of both the average number that will strike it and the number that the probability that a different number, k, will strike it. All right, I'm not going to derive this. So I assume everyone here knows the basic formula for mean and variance. That's probably safe. But there might be some non-engineers watching, and we can do this very, very quickly. So a discrete version of the first one would be if I'm going to cough sometime during a lecture, and it's a random time that I cough because I have a cold, then that formula will let us compute the average time that I cough. So I might cough at minute 1 times the probability that I will cough at minute 1 versus any other time. It's a 75-minute lecture. Plus I might cough at minute 2 times the probability that I'll cough at minute 2, and so on. And that will be 37.5, which is halfway through the lecture. Okay, fairly obvious. And this is just the integral version of that. The variance is how much variation there will be. And so if we just look at the formula, that's going to be 1 minus the average, or the mean, which is that, squared, times the probability of that happening, plus 2 minus, and then et cetera. And that's going to be about 22 for this particular case of coughing once randomly during a lecture. So that's the variance. So I'm just reading off those formulas directly. For the Poisson distribution, the mean is lambda, because that's the way we defined the Poisson distribution. We said the average number of photons arriving is going to be lambda. So that's the mean. What's interesting is that the variance also turns out to be lambda. So I'm not going to derive that here, but you can work it out from the formula that I gave on the previous slide. So if the variance is lambda, then the standard deviation is the square root of the variance. That's the square root of lambda. So that's really important. What that's saying is if I increase the number of photons, in other words, if I increase lambda, that the standard deviation, the variability in how many photons arrive, will also grow, but slower. It'll grow as the square root of the number of photons that arrive. That's the key to reducing noise in photography. Increase lambda. And you can kind of see that here. As I increase lambda, so the peak of these curves is moving to the right, and the shape of them is changing as well. The square root of lambda is not changing as fast. Okay. So the deviation grows slower than the average. So here is how we would define how clean an image looks, the signal-to-noise ratio. And it's very simply going to be the ratio of the mean pixel value, which is the number we read off a sensor, to the standard deviation of that pixel value between pixels or across multiple exposures. And so that's just going to be mu over sigma. And it's typically measured using a logarithmic scale. So 20 log 10 of mu over lambda. And this is in decibels. And so here's an example. If we increase the signal-to-noise ratio from 100 to 1 to 200 to 1 somehow, then it improves by 20 log 10, 200 minus 20 log 10, 100 is 6 decibels. Okay, so let's look at how that applies to taking a picture. So let's go back to photon shot noise. So the photons arrive in a Poisson distribution with this mean and this standard deviation. So the signal-to-noise ratio, by the formula on the previous slide, is going to be this over this. And that is just going to be lambda over square root of lambda, which is the square root of lambda. So the signal-to-noise ratio will go as the square root of the number of the brightness, the number of photons that arrive. So shot noise scales is the square root of the number of photons. So here are some simple examples of applying that. If we double the width and height of a pixel, we'll increase its area by 4x. Hence the number of photons by 4x. Hence the signal-to-noise ratio by the square root of that, or twice, which is 6 dB. So that's a camera that has pixels that are twice as big. Or if we open the aperture by 1 f-stop, so remember 1 f-stop is a square root scale, f-stops, so we're increasing the diameter by a square root factor. That increases the area by a factor of 2. Hence the signal-to-noise ratio by the square root of that, which is the square root of 2. So here's the effect on your image of having bigger pixels or a lower f number.
Don't you need to have increased capacity for each pixel if you double the width and height?
Well, if the pixel is larger, it will have increased capacity. The full well size will be larger if the pixel is larger. Just the way the chip is designed. Okay, so let's do a laundry list here of other stuff that happens. So that's not the only kind of noise. There's also dark current noise. And so what that is electrons dislodged by random thermal activity. It rises with temperature, it rises with exposure time, and it varies across sensor. It is an average amount of dark current, but it's variable as well. And so we say that it has its own shot noise, but don't, there's a blow up of it, but don't confuse it with photon shot noise. The word shot noise just means electronic randomness that follows roughly a Poisson distribution. So there's photon shot noise, there's also shot noise in this dark current. So look, this is kind of interesting here. This is the lower right corner of the sensor, and it's got a brighter spot there. That's some other piece of circuitry or an amplifier, because it's getting hot, and this dark current rises with temperature exponentially. These are all from one particular website, so you can look at it yourself. Excuse me. All right, more laundry list, hot pixels. So hot pixels are electrons leaking into the well due to manufacturing defects. And it could be a partial hot pixel where you get too many electrons as you accumulate particularly long exposures. Or it could just be stuck on. The more common case is just that there's a little bit of leakage and it accumulates too many electrons. This also increases with temperature. It changes over time. Every camera has these hot pixels. There's a blow up. So you can fix both the dark current and the hot pixels in several ways. Oh, here's an example. Let's see. So this is in that Nokia N95 cell phone that I showed before. The full well capacity is 8,500 electrons in each pixel, and the dark current is 25 electrons per pixel per second at a particular temperature, leaking into the pixel. So solutions to this: chill the sensor, because it's exponential with temperature. And that's not as crazy as it sounds. That's what that's what scientific cameras do. And so this is the camera in my microscopy lab at Stanford, the Retiga, and it uses Peltier cooling it's thermoelectric cooling to bring it 25 degrees Celsius below ambient room temperature. Its full well capacity is, of course, larger than the cell phone, but its dark current is really low. Very few electrons leak onto the pixels. So you don't get dark current, and you get relatively few hot pixels as well. Another solution is you can do dark frame subtraction. So take an exposure and then take another one with the shutter closed and subtract the two. And most cameras will do that. So here's the Micro Four Thirds camera, and I've got it set, I think, for a 4-second exposure. So I'm going to put it up close to the microphone so you can hear that. Let's make something really dark. Now it's not going to focus. There. Taking a shot, taking a shot. So it closed the shutter, and now it's accumulating again. It's got a little hourglass. Did you see the hourglass? So it accumulated it for another 4 seconds with the shutter closed. And then it subtracts the two. And many cameras do that. The Canon will do that as well. So another solution, see if I got everything I want to say there. Yeah, so another solution is image processing. Those hot pixels, not for the dark current, but for the hot pixels. Oh, sorry, this also compensates for fixed pattern noise. I'll talk about that in just a moment. So another solution for hot pixels and fixed pattern noise is to accumulate beforehand. So in my See in the Dark app, which I showed when we talked about extreme imaging, you could look for isolated bright pixels and say, that's probably a hot pixel. Everything's dark and then there's just one pixel that's on. That's probably not a scene feature. But it's really hard in that app, when it's really dark, to look for bright pixels, because that's what one frame looks like. It's all full of noise. So you have to accumulate in order to discover which pixels are hot. So I don't know if you can quite see the dots there, but that's what it looks like after you've accumulated for a while. So it's a little tricky to do that on a cell phone because there's no shutter. You can't close the shutter and then accumulate for a while. So I came up with this hack of accumulating during the autofocus. So think about focusing. So there's my Nexus 6P. It's got a little lens that moves back and forth. It focuses. And remember the Gaussian lens formula? When it's focusing, the lens is moving back and forth. The image is breathing a little bit. We talked about that before. That breathing will blur out the image. And so it won't look like any scene feature. And I can look at that image and easily pick out the hot pixels. So if you look at it, it looks all blurry. It's not all just blurry. It's a radial blur. There'll be a sharp spot somewhere in the middle there. and it gets blurrier and blurrier toward the edge because this is the image doing this as the lens moves back and forth. And then I can, so everything's blurry except for the hot pixels. So it's a trick, and then I can replace the hot pixels with the average of its neighbors. And so there it is before hot pixel correction, and there it is after hot pixel correction. So cell phones have hot pixels, and you can remove them. So fixed pattern noise is manufacturing variations across pixels, columns and blocks, mainly in CMOS sensors. They'll typically have a columnar or row structure, depending on what's causing them. Usually, I'll show another example shortly. It's a stronger row structure. It depends on the sensor. And so, again, you can read once and subtract it. You should accumulate for a while. But in this case, you don't need to do it with the same gain. So you can do it with the shutter open. So here is the Nexus 6, and that's the fixed pattern noise on the Nexus 6. It's actually pretty severe. That was last year's phone. But you can accumulate and then subtract. And you can do that with the shutter open. Let's see. Shutter open, very short exposure time is, I guess, actually what I use for that. I don't need to block it, though. Last one is read noise. So that's thermal noise in the readout circuitry. So in a CMOS sensor, the voltage goes down a line and then goes into this analog to digital converter. All of those will have electronic noise, all of that circuitry. And so it's not a fixed pattern, and the only solution then is cooling. So this website was generally pretty good, but I don't believe this image. I see what looked like JPEG artifacts on that image. So caveat on that. So recap, photon shot noise is unavoidable randomness in the number of photons arriving and grows as the square root of the number of photons. So brighter lighting or larger pixels or longer exposures or a wider aperture will all reduce photon shot noise. Dark current is in particular for long exposures. And you can correct by subtraction, which is what these cameras do at long exposures. And then there are these hot pixels and fixed pattern noise, which you can correct also by subtraction. And then read noise, which is unavoidable and you cannot. And so how good a sensor is going to somehow depend on the photon shot noise and the read noise dominantly. And so I'm about to show a big formula for that that puts all those together. But let me see if there are any questions first. Any questions here? So I think, let me just show you the formula, and then I think we'll probably pick up next time. So I showed this already, the ratio of the mean to the standard deviation. Here is a formula that puts all of those noise terms together. You'll see lots of different examples of this. So this is the number of photons over its square root. So there's the photon shot noise. Multiplied by the exposure time. There's the quantum efficiency. There's the dark current, and it's multiplied by time. The longer, the more dark current. And there's that nasty read noise term. So this is a simplified noise expression that kind of shows you where the variables go. So this signal to noise depends on this over its square root. So it depends on the scene brightness. There'll be a different signal to noise ratio for different brightnesses of scenes. The lower scenes, the darker scenes, will have worse signal to noise ratio. Okay, I think I'm going to stop here. We'll pick up with this next time. But next time for this will be Wednesday, and on Monday we'll have Jesse Levinson talking about astrophotography and night photography, and Florian Kainz talking about trick photography and special effects. Okay, so I'll see you next Wednesday.